Welcome back. So in this video, we are going to start Chapter 0, Preliminaries. Chapter 0 contains 4 sections: the axiom of choice, general topology, vector spaces, and norm spaces. In this video, I will cover the first section about the axiom of choice. Now, you may be already familiar with the axiom of choice and Zorn's lemma. We will use Zorn's lemma in Chapter 3. So this is why I started here with a review. And actually, Zorn's lemma is equivalent to the axiom of choice. Now, if you already know this material, the equivalence between the axiom of choice and Zorn's lemma, you may skip this section if you like. You can read it. But I want to be complete. Okay? So there are 3 forms of the axiom of choice. Form 1, the most common, states the following. If we have an arbitrary collection of pairwise disjoint and non-empty sets AI, then we can select exactly one element from each set. So this selection actually forms a new set that we call C. So there is a new set called C that intersects each set of this collection in just one point set. Okay, so now for most of you this seems trivial, and this is why you call it an axiom. Now, why do we do a big deal about this axiom? Because it has some unexpected consequences, as we shall see now. So it's very simple to state. Okay, so we have a pairwise disjoint of sets, and we select exactly one element from each set. Now, in this form, we don't know how to do this selection. So how do we select this element? We have so many choices if the collection is big. So this axiom gives no algorithm, if you like, or no procedure, gives no procedure to the process of selection. It just states there exists, you can select, okay? But it doesn't tell us how we should do the selection, okay? Now, if you remember, we used this axiom to construct a Lebesgue non-measurable set in Math 3301, if you remember, okay? If you forgot, it's not a big deal. Okay, now I must say that due to the unexpected consequences of this axiom, some mathematicians in the beginning of the 20th century refused to use this axiom, okay, because it's not constructive. So it's just an existence axiom. But these days, most mathematicians use it frequently, okay? Now, in this course, we are not going to use it explicitly. We are going to use an equivalent form of it, okay, known as Zorn's lemma. Okay. Now, there are 2 other forms of the axiom of choice. We can restate this actually in 2 other forms. The 2 other forms use the important notion of Cartesian product of sets, and this notion is very important because we shall deal later with product of topological spaces or Cartesian product of topological spaces. So we must understand what is the product of an arbitrary collection of sets. Okay. If you have a finite collection of sets, it's very easy to define the product or the Cartesian product due to Descartes. So Cartesian comes from Descartes. Okay, so if we have a finite collection, A1, AN, then the product, or the Cartesian product, denoted by this symbol, product of AI, I from 1 to n, is by definition the set of n tuples, x1, x2, up to xn, where each component, xk, belongs to capital AK. Okay? So if we have just two sets, so just have A1 times A2, so it's just the set of couples, x1, x2, or xy, if you like. We have three sets, it's the set of, the product is the set of triplets, and so on. Okay. Now, if we have an infinite countable family of sets, A1, A2, etc., so the sequence is infinite, how must we define the product of these sets? So we proceed by analogy, if you like. So instead of finite n tuples, we can define the product as the set of sequences. So an element in the product is just an infinite sequence. It's a list, right? x1, x2, xn, etc., where each component, xk, belongs to capital AK. Okay? So this is straightforward. Okay. And we denote this product as capital pi ai, I from 1 to infinity. Okay. So an element of the product is just a sequence, an infinite sequence. But how to define, what if we have an uncountable family of sets? How to define their product? Okay, we must look carefully at what we did in the countable case. A sequence, as you know, is just a function, can be thought as a function from the set of integers into the union, because each element is in some AK. Okay? So a sequence is just a function from the integers. If we start from 1, it's a function from n star. If we start from 0, then it's a function from n, but you know it's the same thing, just shift. You can start with any index if you like. So a sequence is just a function from the integers to the union of this collection, where the image of each element of each integer is in AI. So we have 2 points of view here, if you like. So we can write x1, x2, xn, etc., but we can also write f of 1, f of 2, f of 3, f of 4. Okay, so, and this point of view is what we are going to follow here. So, because we cannot write really an uncountable sequence, okay, it doesn't make sense. But we can talk about a sequence, a function from the index set, capital I, into the union. So here's the definition. If we have an arbitrary family of sets, capital AI, indexed by an index set, capital I. Okay, so in the previous example, we took capital I equal n star. But this index set could be anything. It could be the real numbers. It could be r times r. It could be anything. So the product, the Cartesian product of this collection is by definition the set of all functions from the index set into the union of these sets, such that the image of every point in I belongs to capital AI. So you have the same index. So f of I belongs to capital I, AI. Okay? And we denote the product by the symbol product AI, I in the index set. So we have now a generalization of the previous definition of n tuples. And a useful way to denote the elements of the product instead of a function. We can write it as a function, of course, but we can also write it as an indexed collection of elements. So we can write it as f or as xi, I, and I, where each xi is in capital AI. So this notation actually is closer to this notation of a sequence notation. Okay? So we have now here a collection of elements, but each element belongs to the corresponding set for the same index. And now, how do you know that the product of non-empty sets is not empty? This is precisely the second form of the axiom of choice. So form 2. If we have an arbitrary collection of non-empty sets, but not necessarily pairwise disjoint, then there exists a function from I to the union such that f of I belongs to capital AI. So otherwise stated, the product is not empty. Okay? Such function is called, or such collection, if you like, xi, is an element of the product. So such function is called a choice function. Okay. So saying that there exists such function from the index sec to the union such that f of I is an AI is precisely the same thing as saying that the product of a non-empty sets is not empty. So form 1 and form 2 are just saying the same thing. Okay, just same item. So the product is not empty if and only if there exists an element in this product, which is just a choice function. Okay. So now, what is the relation between form 1 and form 1? So form 2 and form 3 are, of course, equivalent, but it's not very clear that form 1 and form 2 are equivalent. Because in form 1, we assume that the collection is pairwise disjoint. The sets are pairwise disjoint. Whereas in form 2, we are not assuming this. So there's something to prove here. And this is the first result. The three forms of the axiom of choice are equivalent. Now, as we said, form 2 and form 3 are just the same thing, expressed differently. So we just have to prove that form 1 implies form 2 and form 2 implies form 1. So let us start with the easiest. Form 2 implies form 1. Okay. So recall that in form 1, we have a collection of pairwise disjoint. Okay. So consider a collection of non-empty and pairwise disjoint sets. Of course, they should be not empty because otherwise we cannot do the selection. If one of them is empty, of course the product is empty. Now, by assumption, so in particular, this is an arbitrary collection of sets. Okay, so we are in the assumption of form 2. So, but form 2 tells me that there exists a choice function. So there exists an element in the product, if you like. Call it f. And consider the image of f. Here we have to do a distinction between f and the image of f. Okay, because f is a function, whereas the image of f is a subset of this union. Okay, so not exactly the same thing. So if you consider the image of this choice function, we claim that this is our set, right? So this is this set C intersects each AI in a singleton, just in one element. Okay, how do you prove this identity? Double inclusion. Okay, so I have to prove two things. We have to first take an element. Okay, so first inclusion. This intersection is contained, or okay, the other way around. F of I is contained in the intersection, and conversely, the intersection is contained in F of I. Now, for F, so pick any I, an arbitrary I, index I. Its image, by assumption, because this is a choice function, f of I belongs to AI, because it's a choice function. And f of I belongs to f of capital I, so it belongs to C. So we have one inclusion. So this singleton here is included in the intersection. Now the reverse inclusion can take an element. How do you prove the reverse inclusion? We take an arbitrary element here and prove that it must be in here. So, so take an arbitrary element in the intersection. Call it small a. Okay, what does it mean that small a belongs to C, which is f of I? It means that small a is in the image. So it must be equal to f of j for some j. We don't know, we cannot say that it's I yet, because we don't know that I equal j. So we must, in the beginning, distinguish between the two indexes. Okay, so A is the image of something. Okay, so what do we have? So f of j, which is small a, must belong to ai, okay, and must belong to aj, because f of j belongs to aj because it's a choice function. Okay, so f of j is in the intersection. This is just a. So a is in the intersection, but our assumption states that the collection is pairwise disjoint. So if this intersection is not empty, then I must be equal to j, okay, because they are pairwise disjoint. And we are done. So a is precisely f of j, which is f of I. So an element here is here. So we have a double inclusion. And that's it. So we succeeded if we assume form 2, given a non-empty collection of non-empty and pairwise disjoint sets, we can form a new set, C, which intersects each set in exactly one element. Okay, so this concludes the proof that form 2 implies form 1. Okay, so this is just an exercise in set theory. Okay. Converse or reverse inclusion. Form 1 implies form 2. Consider now an arbitrary collection of non-empty sets, not necessarily pairwise disjoint. How to create a new collection of pairwise disjoint? Okay, we do this trick. We form a new set which lives in a different universe. So for each I, let capital BI be the product, just the product of two sets. Okay, we are not using here the full strength of the axiom of choice. Just the product. This is just the couple. So an element of BI is just a couple. First component belongs to AI. Second component is precisely I. Okay, we can do this because this is, if you like, the finite form of the axiom of choice. So we need the finite form of the axiom of choice, right? So then, as you may check, the BIs are not empty because AI is not empty and this is not empty. But now the BI are pairwise disjoint. Why? Because if BI intersects BJ in an element, the common element should have, the second component should be I and should be J, so I equal J. So BI, if BI intersects BJ, then I equal J because of this trick. Now, by form 1, so now we have a collection of non-empty and pairwise disjoint sets. So form 1 tells me that there exists a set C that meets each BI in a singleton, in one point. Now the intersection, if this intersection is a one-point set, then the element in the set is necessarily of the form xi I, because the second component is I and the first component belongs to AI. Okay, so what do we have here? For each I, we have an element called xi in AI. So this defines a function, as you know from first year, a function from the index set capital I into the union, okay, because, and the image of each I is in capital AI. So this, if we set f of I equal xi, you get a choice function, okay? So we know now that the three forms of the axiom of choice are the same, okay? Now, I'm going to talk a little bit about ordered sets because it's very important in order to formulate Zorn's lemma, okay? Because Zorn's lemma ensures the existence of a maximal element. So what is a maximal element? We need first the notion of order on a set, or partial order if you like. An order relation or a partial order relation on a set X is just a binary relation R, which satisfies, as you know, the three properties: reflexivity, antisymmetry, and transitivity. Okay. Usually, an order relation is denoted by this symbol, less or equal, or curly less or equal. Now, the usage of this symbol is useful sometimes because in order to, so for example, if you work on R, we need to distinguish between, for example, the usual order and another order that you can put on R, because on the same set we can put several order relations. Okay, so an ordered set is just a couple X and an order relation, and a series of quick examples. The usual order on R, N, or Z, just less bigger. Okay, so you know that. This is the usual order that you know from high school. A less trivial order relation, if you consider the set of integers bigger than 1, so starting from 2. I will tell you why I didn't put 1 here. Okay, and define an order relation as follows. So A is related to B. A is less or equal than B if A divides B. Okay, now you probably know that this is an order relation, and if you don't know that, you can check quickly that A divides itself. Okay, if A divides B and B divides A, then necessarily A equal B. Why? Because we are in the positive integers. So this would not be an order relation if you worked on Z, for example, because if, for example, 2 divides minus 2 and minus 2 divides 2, but they are not equal. So this is why we work on the positive integers. Okay. If A divides B and B divides C, then A divides C. Okay, so this is an example of a non-trivial order relation. So we can say that 3 is related to 6. 3 is less or equal than 6 in this order relation, because 3, not because 3 is less in the usual order, but because 3 divides 6. However, 3 is not related to 4 because 3 does not divide 4. Okay, so 3 is less than 4 in the usual order, but not in this order. Okay, now take the same set and define the reverse or the inverse order relation. So A is related to B if B divides A. So here we have 6 is related to 3 and not 3 is related to 6. Okay, so as you may check, this is also an order relation. It's the inverse order relation of the previous example. And more generally, if we have an ordered set, we can define the inverse order relation R minus 1. So A is related by R minus 1 to B if B is related to A by R. Okay, just symmetry. Okay. So if R is denoted by this symbol, curly less or equal, then R minus 1 will be denoted by curly bigger or equal. Okay, another less trivial example of partial ordering, order or ordering, same thing. If you have a set and consider the set of all sets of X, so it's called the power set of X, the collection of all subsets of X. And consider the inclusion relation among subsets of X, so among elements. So the elements of this set P of X are subsets of capital X. So here again, you have an order relation because A is contained in itself. If A is contained in B and B is contained in A, then A equal B. If A is contained in B and B contained in C, then A is contained in C. So this is, but it's not a total order relation. Now I will talk about total order a little bit later. Okay, another less trivial example. If we have two arbitrary sets X and Y, and now consider the set of functions F defined not on all of X, but defined on a subset of X. So it has a domain. So each function has a domain. Okay, and the domain may change from function to function. Okay, so if we consider the collection of all these functions, then you obtain a new set. The elements are being functions now. And now, what is the order relation? What does it mean that F is less or equal than G, or F is related to G? So it's a definition. F is related to G if the domain of F is contained in the domain of G, and f equal to g on the intersection, so on the smaller one. So otherwise stated, what does it mean? It means that g is an extension of f. So it's the same function mainly, but it's defined on a bigger subset. So we say that it's an extension, or you may say continuation if you like. So once again, you can check that it's an order relation because f is an extension of itself trivially. If f is related to g and g, if g extends f and f extends g, then we have a double inclusion. So they have the same domain and they are equal. So they are equal. They are equal on their common domain. So it's the same function actually. And transitivity, if g extends f and h extends g, then h extends f. Okay. So this example actually is very, very important in analysis, because most of the applications of Zorn's lemma, when we seek maximal elements, a maximal element, I will talk about it a little bit later, but a maximal element is a non-extendable function. So this is the most important example in analysis, actually, the order of extension. Okay. Now, last example, if you consider the set of continuous function from an interval of r into r. So here they are continuous. You put the assumption of continuity. This is also a very good example, typical example in analysis. So here again, we use the same thing, but here instead of just extension, we put continuous extension. So we need continuity here. Okay, so once again, this is an order relation on the set of functions. Okay, but each function has its own domain. Okay. Okay, now we say that if you have an ordered set, we say that two elements are comparable if one is related to the other. So A less or equal than B, or B is less or equal than A. This is not true for every relation, for every order relation. Okay, if every two elements are comparable, we say that the order is total. And now I'll give examples, but not all. Keep in mind that not all order relations are total. Okay, so for example, in example A, the usual order of R is total. R, Z, or N, same thing. Okay, so any two elements are comparable. One is bigger than the other in the usual order. The examples B, C, and E, the order are not total. So B, the division order is not total. Okay, because 3 does not divide 4, and 4 does not divide 3. So 3 and 4 are not comparable. Same thing in C. So it's a partial order. It's not a total order. Okay. Same thing for E. In example, in the inclusion, not any two subsets of X, one contains the other. Okay, because you may have two independent sets. Okay, so just draw a picture. Okay, and same thing for F as well. Not any two functions are comparable. One is an extension of the other. Okay, now the biggest element, as you may know, the biggest element, as its name suggests, is an element A, which is bigger or equal in the order relation than any other element. Okay, same thing for smallest element. And when there is a biggest element, it's necessarily unique. Why? Because suppose that you have two biggest elements, A and B, then you get A less than B because A is the biggest, and B is and B is less or equal than A because A is the biggest. So by antisymmetry, A equal to B. Okay, and we have also the notion of smallest element, same thing. And now we come to the important notion of maximal and minimal elements. Okay, we have to do, it's very important to distinguish between maximal and biggest. Okay, not the same thing. So in an ordered set, a maximal element is an element satisfying this relation, an element A. if it happens that a is less or equal than x, then necessarily a is equal to x. So otherwise stated, I cannot have a strictly than x. There is no x which is strictly bigger than a. Okay, but this once again does not mean that a is the biggest element, because the order did not be total. And now I'll give examples. So examples in the division in example C, which was about the inverse division relation. So A is less than B if B divides A. Then what are the maximal elements? The maximal elements are precisely the prime numbers. Why? Because a maximal element is not divisible by any other element. So if and only if, actually, as you may check. Okay, so there's no biggest element here in this case because the order is not total. Yes, there are infinitely many maximal elements. All the prime numbers are maximal for the relation A related to B if B divides A. Okay. Now, if you consider the example B, A divides B, then the prime numbers would be the minimal element. Okay, not the maximal element. So actually, if we reverse the order, maximal becomes minimal and biggest becomes smallest. Okay, just symmetry. If you consider the problem of extension of a function, a maximal element in the set of functions is a function which has no extension in the okay, so cannot be extended. In example G, when we deal with continuous functions, if you consider the function 1 over x defined on 0 infinity, of course it's continuous, but this is a maximal element. Why? Because we cannot extend 1 over x by continuity to a larger interval. Okay, of course we can extend 1 over x to r star, but r star is not an interval. And the problem is that the limit of x as x tends to 0 is plus infinity. So we cannot, there's no way of continuing the function by, right, in a continuous way. And same thing, len of x is also another maximal element. Okay, so we have so many maximal elements here. So len of x is not extendable to a continuous function to an interval bigger than 0 infinity. So these examples are very important. So for us analysts, maximal most of the time means non-extendable. And non-extendable, once again, does not mean biggest, because there need not be a biggest element. And however, to give another example, counter example, if you like, if you consider radical x defined on 0 infinity, radical x is not a maximal element in this order, because you can extend radical x in so many ways to the whole line. You can extend it by 0, you can extend it by x, you can by x squared, anything you like. As long as they agree at 0. So 1 over x and len of x are maximal, but radical x is not maximal. And any function defined on the whole line, any continuous function defined on the whole line, is indeed a maximal element simply because there's no set bigger than r in R. Okay, so when the domain is the full set, then we of course have a maximal element. But once again, this maximal element need not be a biggest element. So I cannot say that there is this function bigger than all the others. Otherwise stated, there's no function which is an extension of all other functions. It's not true. Last example, if you already know topological spaces. If you don't know, you can disregard this example because we shall not need it. But this example is very important, 3. Okay, so 2 and 3 are very important. Okay, but curiosity, if we have a topological space and consider the set of all connected subsets of X, and we order it by inclusion, we have therefore an ordered set, then a maximal element is precisely a connected component. Okay. I will not explain this in details because you just have to go back to the general topology course where you define connected components. And by the way, you can take it as a definition if you like. So because it's equivalent. So a connected component is by definition a maximal element. So it's not contained strictly in a bigger connected set. So it's the biggest connected, well, it's not the biggest, but it cannot be contained in a bigger connected set. Okay. Now, as we said, if the order relation is total, then a maximal element is necessarily unique and it's the biggest element, but in this case, it's not interesting at all. So maximal and minimal elements are interesting precisely when the order is partial. Okay, and now last notion before we state Zorn's lemma, upper bound. As you know from first year, you work with upper bounds and lower bounds in R, but we can extend this concept to an arbitrary order set. So an upper bound is just an element M which is bigger or equal than all other elements, but not so. A set is bounded from above or has an upper bound if we can find an element M which is bigger, but not the M is not necessarily in A. So we are not saying that M is the biggest element because M is just in X and not in A. Okay. And we can give such examples in R already. For example, minus infinity 0 open is bounded from above by 0 or by 1, but it doesn't mean that 1 is in the set. Okay, so we have the notion of bounded from above and of course bounded from below, same thing. And what does it mean that an ordered set is inductive? An ordered set is said to be inductive if every totally ordered subset, and we call this a chain. So if every totally ordered subset of X has an upper bound or is bounded from above. Okay, and now I'll give examples and counterexamples. So this is very important to understand Zorn's lemma. Okay, the notion of, so totally ordered subset, you can call it also a chain. So any two elements are comparable. So R with the usual order is not inductive. Why? Because if you take the subset R itself, it has no upper bound. Okay, because infinity is not in R. Okay, or if you take 0 plus infinity, it's not bounded from above. Yeah, sorry. Okay, yeah, so just yeah, same idea. But if you take just one collection, here we have to take a totally ordered. Yeah, that's it. Sorry. Okay, so we found a totally ordered subset. For example, R is totally ordered of itself, but it has no upper bound. 0 infinity is a totally ordered subset and has no upper bound. Or if you take the set of integers 1, 2, 3, n, etc. Okay, it's a totally ordered subset of R in the usual order, but it has no upper bound. Now, second example, if we consider the set of all, the power set of a set, P of X, and equip it with the inclusion relation, this set is inductive. Why? Because if we consider any subset of P of X, okay, whether totally ordered or not, then any element of A is contained in the union. So the union is an upper bound. And once again, I'm not saying that the union is in calligraphic A. Okay, but so this is just so this is trivial actually. Less trivial example, the set 2, 3, 4, etc. in the relation of so A is related to B if B divides A. This is also inductive. Okay, it's a very good exercise. I want you to pause the video and try to prove this. So I have to consider a totally ordered subset of X. and cannot be X itself because X is not totally ordered, as we said. But we have to take a subset which is totally ordered. Okay. For example, 3, 6, 12 is totally ordered, right? Because we can arrange it. 3 is less, or yeah, so 12 less than 6 less than 3 in this order because it's inverse. So okay, but now I'll give you the proof. So consider a non-empty totally ordered subset of X. Okay, the P is a subset of the integers, but the set of integers, as you know, every subset of the integers, of the positive integers, has the smallest element. Okay, in the usual order, not in this order, in the usual order. This is the so here we have two orders on X. The division or inverse division relation and the usual relation. So we use two symbols. You know that any subset of n has a smallest element. Okay. This is okay. I will not prove this, but because we have to construct the n, but I will assume it. So P has the smallest element x0 in the usual order. Okay. So for every x in P, x is bigger or equal in the usual order than x0. Okay. So x0 is at least 2. We don't know what is x0. It exists. And now consider an arbitrary element x in P which is different from x0. Since P is totally ordered, and of course this is relation is totally ordered, but we are talking about the division relation. The division relation, the P with the division relation or inverse division relation is totally ordered. So either x0 is so either x divides x0 or x0 divides x. This is the assumption of total ordering. Okay, so I'm not saying that x is totally ordered. I'm considering a subset of x which is totally ordered. Okay. Now we know in the positive integers, a divisor is less than the number it divides. Okay. So we have two alternatives here. Suppose first that x divides x0. Then x is strictly less than x0 in the usual order because it's different from x0. Okay, so it's less or equal, but not equal, so it's strictly less. Okay, so we have to make the difference. So this is not the same thing at all. Okay, but this is impossible because x0 is the smallest element of P in the usual order. So the first assumption cannot hold. So necessarily x0 divides x. Okay, x0 divides x. So x is related to x0. Okay, and since x was arbitrary, this means that in P, so we have now an upper bound of P. So x0 is an upper bound of P. Right, and it happens that x0 is in P, so it's the biggest element. And that's it. So we proved that every non-empty, every chain in X has an upper bound, x0. And this upper bound, how to construct it, is the smallest element of P in the usual order. So X with this relation is inductive. Okay, if you didn't understand this example, don't worry. We are not going to use it. And last example, in the connected component example, the set of connected components ordered by inclusion is also inductive. Okay, I wrote the proof, but I'm not going to use it, so it's optional. Oh, okay, so, but here's the same idea. So just consider a collection, a subset of C. So a collection of connected subsets of X, but which is totally ordered. So one is contained, any two elements, one is contained in the other. So you may prove that the union of all these elements in calligraphic A is also connected. Not totally trivial, but you can prove that. Okay. So this union is connected and so belongs to C. So we have an upper bound. So this element here is an upper bound of calligraphic A. Okay, once again, if you didn't get it, don't worry. We are not going to use it any time in this course, just for completeness, curiosity. Okay, and now we are ready to state Zorn's axiom or Zorn's lemma. It's most known as Zorn's lemma. Any non-empty inductive set has a maximal element. Okay. So to prove, if you want to seek a maximal element in a set, we must prove that the set is inductive. Otherwise stated, we must consider a chain or a totally ordered subset and prove that it's bounded from above. It has an upper bound. Okay, so once again, this axiom is an existential axiom. It tells me a maximal element exists, okay, but it doesn't tell me how to construct the element, how to approximate it, or how to construct it. And finally, the notion of well ordering. I will not use it in this course, but just to be complete, an ordered set is well ordered if every non-empty subset of E has the smallest element. And the most famous example is the set of integers is well ordered, and we used this fact actually in the previous example. So n is well ordered. So any non-empty subset of n has the smallest element. We used this fact. However, Z and R are not well ordered because you may consider so Z has no smallest element, right? Or the negative integers have no smallest element. Same thing for R. So n is well ordered in the usual order, but Z and R are not. And the well ordering theorem states that on every set we can put a total order relation or total ordering relation. Okay, so this is known as Zermelo's axiom, or sometimes as the well ordering theorem. And it states that any non-empty set can be well ordered. We can put an order relation on this set. But once again, this is as well an existential axiom. Okay, it tells me there exists a well ordering relation, but it doesn't tell me how to construct it. Okay, and the main result of this video, of this section, is that the axiom of choice in any form you like, Zorn's lemma, and the well ordering theorem are equivalent. So if we accept all the other axioms of set theory, we can prove that we can deduce Zorn's lemma from the axiom of choice and vice versa. And we can deduce Zermelo's theorem from the axiom of choice and vice versa. So if we assume the axiom of choice, then Zorn's lemma becomes a theorem and Zermelo's theorem as well. If we take Zermelo's theorem as an axiom, then the axiom of choice would be a theorem. Okay. Now, to conclude, now the proof, well, first of all, it's not a part of your program, and it's a little bit complicated. So I will give you a reference. You can find a proof in the book of Bourbaki, Elements of Mathematics, but it's a little bit difficult to read. An easier proof can be found in the book of Halmos. It's more readable, the small book. If you are really interested in the foundations of mathematics and logic, you can read the proof. I'm not going to do it. And actually, few mathematicians know it. Okay, so you can be an excellent mathematician without knowing the proof of this theorem. In this course, all we need is the possibility of application of Zorn's lemma. Okay, this is all what you need. So this concludes this video. If you didn't understand everything, don't worry. So in chapter 3, you are going to apply to use Zorn's lemma. Okay, in order to prove the existence of a maximal element, we will be using Zorn's lemma. So we are going to consider an ordered set and then prove that a chain of the set is bounded from above, and therefore by Zorn's lemma we have a maximal element. This is all what you need to know. And I think that you already know this. In principle, you should know this from courses in algebra, okay, where we use Zorn's lemma a lot, more than the well-ordering theorem. Okay, so all I wanted to say in this video is that the axiom of choice is equivalent to Zorn's lemma. Okay, so thank you for your attention and see you on the next video about topological spaces.